So what do we mean by a linear dynamics model? Well, it's pretty straightforward. A linear dynamics model says that our state at time t will be distributed according to a normal distribution whose mean is just a linear function of the previous belief. Okay, so D here is it's either a scalar or a matrix, depending upon whether X is a scalar or a vector. And then we take that and we put some Gaussian noise around it, some covariance. And by the way, you'll notice this little t here on these D's, okay? What that says is it could be that our dynamics model changes over time. That is, the actual multiplication that we do might change, but we assume we know it. So I'll tell you the vast majority of Kalman filters, those D's are constant, so that the transformation and this thing here, which is referred to as the process noise, is constant. All it's absolutely required is that it's known for every time t. So that's the linear dynamics model. We're going to do an example of that in just a minute. We also assume a linear measurement model, and that looks stunningly similar. Right? What that says is that the measurement we'll get will be some Gaussian normal distribution that's about some linear, M here is a measurement matrix, that linearly multiplies the state, and that the measurement noise is also a Gaussian. And again, it's subscripted by t because it could vary with time, but we assume that it's not. So what I haven't mentioned is that this x, both on this slide and this slide, those x's are unknown. We don't remember, it's the hidden state. We don't actually know what the state is. But we're saying is that this is how our linear dynamics model works.